one of the important aspects when you think about the vibrational energy level is the comparison with the thermal energy, which means even if the molecules are just staying in your room and at room temperature, there are many exchange of the thermal energy defined by the temperature there. So which correspond to the KBT, so Boltzmann constant times temperature. And room temperature, which is around 200 Kelvin, right? So this amount of energy is easily exchanged during the daily life. So any molecules can exchange this level of energy if they are in the room temperature. And what we are thinking about is vibrational energy. And vibrational energy is, for example, it's like typically like say 500 to 4,000 Kelvin in many cases, which is larger than the thermal energy at room temperature, but actually not so much large compared with thermal energy. So due to the sum of the Boltzmann distribution, which means the thermal distribution of the state, some of the molecules are sometimes excited, but mostly not. So that's the vibrational energy amount compared with the thermal energy. Okay, and especially for, you can easily imagine that KBT is proportional to temperature. So when the temperature is higher, in many and smaller vibrational energy can be easily excited. Okay? So again, most of the vibrational energy is larger than this. So most of the vibrational state is at the ground state. So ground vibrational energy level. That's please keep in mind that. And similar as the rotational energy, rotational transition, and there's some transition rule for the vibrational transition too. And the rule is, one of the rule is on the vibration, molecular dipole should be changed, right? So compared with the rotational transition, somehow a little bit different. This on vibration is added here. So in the case of rotational transition, the permanent dipole in the molecule must be there. But here, during the vibration, this molecule need to have a dipole. Here's one of the typical example here. So originally, there's 3 atom molecules does not have the total dipole because it's symmetrical. But when it's vibrate like this angle changing vibration, it could have the dipole during the vibration. So that's the necessary condition, right? So, for example, the homonuclear molecules, in the case of, for example, like nitrogen. So this molecule, you cannot have permanent dipole nor the dipole during the vibration. So you couldn't have any transition in the case of the homonuclear molecules. And in the case of linear molecules, like, for example, CO2 or H2O, I don't know, linear molecule is the CO2 case. You can have, during the stretching of the oscillation, you can have the dipole during the vibration, right? So that's why the stretching oscillation you cannot have. But if this one is under the bending or motion, like this figure, it could actually have the vibrational transition. So always when you need to understand if this molecule has a vibrational transition or not, you have to think about the motion during the vibration. And the other rule is the same as the rotational transition. The vibrational quantum number must be changed step by step, so one by one. Not, you cannot jump from 0 to 2 or 1 to 3 or something like that. So then other important aspect in terms of the vibrational energy is the unharmonicity of the potential. So what it means, so we assume the vibrational potential as parabolic term like this. So what I mentioned is here. So we just assume as equilibrium position, the potential has a parabolic form. But actually, by assuming this, there could be have an infinite number of states, because what it means is we could obtain the energy level V plus half times h bar omega, and V can be any number from 0 to infinite, meaning that energy can be infinite, right? So any larger energy you could take for the vibration. But of course, it's impossible. So if you think about the molecule connected with a spring, and any larger energy, meaning the very fast oscillation, could possible. That's impossible, right? So this is because we assume the potential is like parabolic, but this one is actually not true. And as you see in this figure, the real potential is not like this. Parabolic is only acceptable around the equilibrium position, but actually potential looks like this. And to modify the realistic, to make it realistic potential as a second approximation, we frequently use a Morse potential. And this potential is given as HCDE, like 1 minus exponential minus A R minus RE. And you don't have to go into the detail of this equation, but just imagine the shape of this potential. Effective omega squared to HCDE of half. And then now the potential is, in the case of the always larger, this exponential term is going away. So leaving approach to 1. So this one is going to so how is larger? Oh, this one is going to 0. So it's coming to some constant value. So it's more like this shape. And by using this potential, you can obtain the vibrational energy in Kaiser, which is, if you're interested, please check some of the textbook. So GB in Kaiser can be given like plus half U the order minus V plus half squared XE mu to order and XE equal given by 2 times effective omega A squared H. Well, like this. So you could find that now you have some additional term here. So which reduce gradually as increase in the V value. This one is reducing the interval of energy, which makes as approaching this way, this interval is gradually smaller by this time. So even if V increases, the energy is somehow converged. So that's more like a realistic approximation of the vibrational energy.